Hello, everybody. Today we're going to be going over Unit 1 of Dual Enrollment Chemistry. I have had a little bit of requests for this video, so I am now making it as finals are coming up. So, Unit 1 of Chemistry is all about the atom and how light, particles, and parts of the atom behave. So, I will have all of the topics in the timestamps of the video. Feel free to skip to any topic that you particularly want to look at. And let's get started. So, first, electromagnetic radiation. This has to do with the concept of light. Now, here's the electromagnetic spectrum. The electromagnetic spectrum shows the range of all different wavelengths of light that can be emitted. Now, we can't see all of the light, we can only see the visible light, as the red, orange, yellow, green, blue, indigo, violet. Those are the colors we can see. However, if, for example, we try to look at the gamma rays, they're so small that us humans can't see them. And radio waves are so big that we also can't see them. So, there's only a little bit of range where we can actually see visible light. In other words, large objects are going to have very big wavelengths, and super small objects, like atoms and protons and neutrons, are going to have super small wavelengths. And that's mainly all you need to know. Next, we're going to talk about wave-particle duality. So, light acts like both a wave and a particle. And this was found out through what is called the double-slit experiment. I'll put the experiment infographic on screen, but you don't need to know the specifics of the experiment. All you need to know is that this experiment was the one that saw light as a wave and light as a particle. Another thing that also proves the wave-particle duality of light is the photoelectric effect. In other words, if light is shining down on a surface, let's say the surface is a charged surface like a metal, this electromagnetic radiation will, in most cases, emit electrons. So we'll use these as minus signs. So it's going to emit electrons depending on the voltage of the light and the surface. So let's go over a few examples of how that could work. A great example of the photoelectric effect is when electrons move to different energy levels in the atom. So the Bohr atom looks something like this. Okay? So if an electron moves from, let's say, we call this the third energy level, down to the second energy level, this is going to release energy. So it's going to be an energy relaxation. But if we have another electron that goes from energy level 1 to 2, this is going to be an energy excitation. In other words, we're going to absorb energy. So, what this all means is that when we're emitting energy through relaxation, we're returning it to a ground state electron. And it's going to emit a photon. And the photon that it will emit is going to have a wavelength or color, it corresponds to the energy difference between the two levels. So depending on which levels it goes from, it depends on the color that it's going to give. Now, for absorption of energy, when the electron absorbs energy, it moves to an excited state. The energy of the photon must exactly match the initial and final energy levels, meaning that nothing's emitted. So it makes the electron less stable. So, in conclusion, energy transitions are meant to explain the fluorescence of items and how materials absorb and reflect light, depending on wavelength. So, a few examples of this are, imagine if we went from energy level 6 to energy level 2, compared if we went to energy level 4 to energy level, let's say, 1. Which of these would have a higher energy emitted? In this case, it would be energy level 6 to energy level 2, because we're moving down more energy levels, i.e. we're emitting more energy. Now, imagine we went from energy level 1, energy level 2, or energy level 3 to 4. Now, which of these will emit the most energy? That would, in fact, be 1 and 2. And the reason is because the farther up you go in the energy levels, the more that is absorbed. So 3 to 4 will absorb much more than 1 to 2. So those are a few examples on electromagnetic radiation, photoelectric effect, and wave-particle duality. Now, let's move on to the more important part, the part 2 of this unit. Okay. For this section, we're going to be talking about electron configuration. So, electron configuration is simply the configuration of electrons in an element. So, for example, if we want to find the electron configuration of, let's say, carbon, we're essentially going to find the coordinates to the element. So a few things you have to know are the different blocks on the periodic table. So this right here, these things are the S block. The transition metals are the D block. This is the P block. In fact, hold on. This is the P block. Helium is included in the S block, by the way. And then this down here is the F block. Okay? So, we're going to use this knowledge to now tell where the electrons are located in carbon. So, for carbon, the electron configuration, we're just going to go, how electron configuration works is that we're just going to go by the row of the periodic table. So there's 7 rows of the periodic table. So hydrogen is the first one. So hydrogen is going to be in the first row. We're going to be in the S block, and we're going to have 1 electron. So you raise it to the first power. Okay. And then now we go to helium. We're still in the S block, but we've added another electron. So now we go 1s2. Okay. Now we're on to a whole new row with lithium. So we're at 2. We're still in S, and we've added 1 electron. So now we have 3 total electrons, which is lithium. Now for beryllium, we have to add another electron, so 2s2. Next would be boron. Boron is in the P block, which is in the second row. And we have only 1 additional electron. And as you can see, the superscripts, 2 plus 2 plus 1 is 5, and 5 is the atomic number for boron. So that's how you can check if everything's correct. And then for carbon, we just have to add one final electron. So 2p2. So this is the official electron configuration for carbon. 1s2, 2s2, 2p2. Let's try another example. Fluorine. For fluorine, I will start you off with 1s2, 2s2, and then what comes after? I'll give you a few seconds to answer. You can pause the video if you need more time. So, the correct answer is 2p5. Because you have 1, 2, 3, 4, 5 added electrons in the p orbitals in total. Now, let's try another one. Let's say silicon. For silicon, I want you to write out the full electron configuration. I'll give you a few seconds. So it'll be 1s2, 2s2, 2p6, 3s2, and then it'll be 3p2. So this is the electron configuration for silicon. Now, there are some important exceptions and important things that we need to follow using this electron configuration rule. The usual confusion comes along with the higher levels of higher atomic numbers. And because we don't have all day to write all of those letters and find out the orbitals, there's something called the noble gas notation that will help us easily be able to write the electron configuration. So imagine you want to find the electron configuration of, let's say, calcium. What you do is that you just put the most recent noble gas. In this case, the noble gases are going to be in the final row of the periodic table, so helium, neon, argon, krypton, xenon, radon. And so for calcium, argon is going to be the last noble gas. And then you continue along with the electron configuration. So calcium's in the fourth row, and we're in the s block, and he's the second electron. So this would be the electron configuration for calcium, using noble gas notation. Now, a super important thing to note is that when you get to the D block, the transition metals, this row right here, you would think is the fourth row. This is actually the third row. This is the fourth. This is the fifth. And this is the sixth. And in other words, this is the fifth, and this is the sixth, because this is in place of these little purple and pink squares in here. So, let's say we want to find the electron configuration for, let's say, nickel. So, for nickel, we have our most recent noble gas is argon. And then we have a full 4s2. And then, instead of 4d, we have 3d. And then, now we just count how many electrons. In this case, it's going to be 8. 3d8. So this is the electron configuration for nickel. Now, I want you to try one of these on your own. Find the electron configuration for yttrium. If you don't know where yttrium is, it is atomic number 39. Okay, so yttrium, the most recent noble gas, it would be krypton. Then we have 5s2, because the s orbital is full. And then we'll have 4d, and will be the first electron, so 4d1. So this is the electron configuration for yttrium. Let's try one more example with lanthanides. So, what is the electron configuration of erbium? So, the most recent noble gas is xenon. And then we'll have 6. We'll be in the 6th row. We'll be in S. And the orbital will be full. And then, instead of the D's, we'll have the F's. So after 6s2 will be 5f. And then now we simply count. Now, a shortcut to know is that there are 14 electrons in the f orbitals in total. So we can just count backwards. So LU will be 14, YB will be 13, TM will be 12, and then ER will be 11. So, in other words, this is the electron configuration for erbium. Xenon 6s2, 5f11. So, that is how you find the electron configuration of an element. Another important topic in Unit 1 of chemistry is effective nuclear charge. So, what is effective nuclear charge? Well, effective nuclear charge has to do with electrons compared to shielding electrons, which the reason why shielding electrons and these electrons are important is because the numbers of valence electrons are what contributes to bonding, which is what you would learn in, let's say, Unit 2 of this course. So, to understand how bonds work, we first have to understand effective nuclear charge. So, effective nuclear charge is essentially the net positive charge experienced by an electron in an atom. And so, we're essentially comparing the core electrons and the valence electrons. So, let's say we have an atom of aluminum. Okay? We want to find the effective nuclear charge. So, in other words, we want to find aluminum's attraction of electrons to its nucleus, which impacts the atomic radius, the ionization energy, and electronegativity of aluminum. So, let's find the effective nuclear charge. The best way to do this is just to draw a picture of the Bohr diagram for aluminum. So, aluminum has 13 electrons and it has 13 protons because it is atomic number 13. So, it'll look something like this. There's 2 on the first level, 8 on the second, and there's going to be 1, 2, 3, with a total of 13 electrons. So, the formula for effective nuclear charge, which is denoted as Z with the subscript EFF, is going to be equal to the number of protons minus the shielding electrons. So, in other words, the shielding electrons are just the core electrons. So, for energy level n equals, let's say, 3, for n equals 3, we have 3 electrons on the outside, and we have 10 on the inside. So, we would say that we have a total amount of protons of 13, and we subtract the inside, 10 of them, 2 on the first energy level, and 8 on the second. And then we get an effective nuclear charge of 3. So this is the answer. Now, let's try another example. What is the effective nuclear charge of nitrogen? I'll give you a few moments to find out the effective nuclear charge. So, the effective nuclear charge of nitrogen is simply going to be the amount of protons it has, which is 7, minus the shielding electrons. So, according to the periodic table, nitrogen will have 5 valence electrons. In other words, it'll have 2 core electrons for a total of 7 electrons. Because remember, the electrons and protons are the same in a neutral element. So we'll have 7 minus 2, which equals 5. So this is the effective nuclear charge of nitrogen. Okay, now let's talk about quantum numbers. So, quantum numbers, just like electron configurations, are unique to every single element on the periodic table. The quantum numbers are going to be L, are going to be N. Here, let me actually write those in different order. N, L, ml, and ms. So the n value corresponds to essentially the row on the periodic table that the element's in. So the n value would be 1 for hydrogen, for magnesium it would be 3, for barium it would be 6. It just depends, obviously, which element you're talking about. For L has to do with the orbitals and blocks that we talked about earlier. So our SPDF, we assign SPDRF to 0, 1, 2, and 3. So for example, hydrogen will have an L value of 0, iron will have an L value of 2, and einsteinium will have an L value of 3. Now, for the ml value, this is simply going to be the plus or minus the number that we got from L. So this represents the orbitals, the possible orbitals of an element. So if we had an as L equals 0, then our ml will also equal 0. But if we had, let's say L equals 1, then we could have 3 different possibilities: a spot -1, 0, and 1. And then if we had L equals 2, then we can have -2, -1, 0, 1, and 2. And the pattern continues. For F, we can have -3, -2, -1, 0, 1, 2, and 3. So these represent all the different positions of the orbitals. And as you can see, we can see that S, or not S, P has 3 orbitals, S has 1 orbital, D has 5 orbitals, and F has 7 orbitals. So that's the conclusion that you need to draw from the ml value. So it is essentially plus or minus the L value. And then our ms value can either take on 2 forms: positive 1/2 or negative 1/2. This is just the spin of the atom. In which direction is the spin? And the way to tell that is by drawing an orbital diagram. So let me subside all of this and let me show you how to draw an orbital diagram. So we'll have our energy 1s, 2s, 2p. Let's say we want to find oxygen's atomic quantum numbers. Okay, we'll have an N value, we'll have an L value, we'll have an ML value, and we'll have an MS value. So the 1s orbital, as we've discussed, the s orbital only has 1 orbital, so we'll have 1. Same thing with the 2s, but the 2p orbital will have 3 different orbitals by 6 total electrons. So 1, 2, and 3. So the rule that we're following by going in order, these rules are in the order of, in the order of the orbitals. This is called Aufbau's rule. And you'll need this on the test. All this means is that we're going in the correct order of orbitals. So we're going from 1s to 2s to 2p. Imagine we go now to 3d after this. Right? We'll be skipping the 3s orbital and the 3p orbital and the 4s orbital. So we would be violating Aufbau's rule. So you will sometimes be asked, what orbital diagram or what different rules does this orbital diagram essentially violate? So Aufbau's rule, the first one, is that the orbitals have to go in their correct order as they are on the periodic table. So how to write an orbital diagram is we're going to alternate putting up spin and down spin on our atoms, or in our orbitals. So the first electron will have a positive spin. The second will have a negative spin. So they're going to cancel each other out. We'll have a positive spin and a negative spin. Now, a rule that you have to consider is Hund's rule. Hund's rule. Hund's rule states that we need to put an up-spinning electron in all of the orbitals before we can put the down-spinning electrons. So, if we wanted to do oxygen is atomic number 8. We've already done 4 electrons. So, when we put our 4 electrons, we put 1, 2, 3, and then with 4, we put down. Okay. So now we can determine the quantum numbers for oxygen. So for oxygen, this is going to be in the second row. It's going to be in the P block, which means it's going to be L equals 1. The ML value is going to be plus or minus 1. It's just plus or minus the L value. And then we see here that this right here is going to be a down. So we're going to have a negative 1/2 spin. So these are the quantum numbers for oxygen. Next, we have the concept of isoelectronic ions. So when it comes to these, it's super, super simple. It just means that our elements have the same amount of electrons as each other. So, of course, on the periodic table, all of these elements in their neutral state have a different amount of electrons, as they're the same as the protons, which define the element. So, if we were to say we had, let's say, calcium 2+, we would be saying that we're adding 2 electrons, or we're subtracting 2 electrons, or in this case, adding 2, or we're subtracting 2 electrons, and so this would be basically the same thing as calcium, and then you take away 2 electrons, so potassium, and then argon. This would have the same amount of electrons as a neutral argon. Okay? And vice versa. If we have argon 2-, we'll be gaining 2 electrons, because remember, electrons are negatively charged. So if we have 2-, that means we're gaining 2 electrons. This would be equivalent to or neutral calcium atom. So, in other words, the electron configuration for Ca2 plus and argon is the exact same. So that's mainly all you need to know. Sometimes they will ask you a question, which of the following is isoelectronic to this electron configuration, and you'll have to find out which one has the same amount of electrons based on the charge of the ions. Now, let's get into our last section, magnetism. So, to determine whether an atom is paramagnetic or diamagnetic, we have to look at the orbital diagram. And so, for paramagnetic atoms, we'll have unpaired electrons. But for diamagnetic, we'll have all paired electrons. So, for example, if we wanted to find out if fluorine was diamagnetic or paramagnetic, we would have to draw the orbital diagram. So, in this case, we'll have 1s, 2s, and 2p. S and 2p. And then we simply remember to follow Hund's rule as we're doing this. And also, it's a good thing to know that there's such thing as the Pauli exclusion rule, Pauli's rule, where we can only put 2 electrons in an orbital. One with a plus half spin and one with a minus. So, you will be following Pauli's rule, and you will also be asked of on the test. So, let's follow Hund's rule now and fill these. So now we have a total of 9 electrons, which is fluorine. And the thing is that if we look over here, we have an unpaired electron. So that means this is going to be paramagnetic. And what this means is it's going to be attracted to a magnetic field. In other words, it wants to pair with another electron to fill the orbitals. Now, if we had, for example, let's say sodium, or no, not even sodium, let's say neon. If we had neon, we would have 1s, 2s, 2p, and then for our structure, we would have something like this. We would have 0 unpaired electrons, because all of these guys right here have a partner. So they would be diamagnetic. In other words, they will not be attracted to a magnetic field. Anyway, I hope you liked this video. This video took a lot of effort to make, so I would appreciate a like and a subscribe. That's what I need from you, Patricia, if you're watching this video. I don't know who Patricia is, but hopefully somebody watching this video is named Patricia. You better hit, if your name's Patricia, you better hit that like button. You better hit the subscribe button. And I will see you all next time for another chemistry, math, physics, and whatever video. Goodbye.